Okay, hi everyone. So let's talk about errors. So what is the importance of errors and how do we find the errors? So what is the importance of errors in numerical methods? So in numerical methods, we will always deal with errors since in numerical methods, we are not usually finding the solution or the true solution. We are just approximating the solution. So therefore, it will always be introduced inevitably. Okay, so what is error? It is just the difference between the true value and the approximate value, basically. But we could expand on this later on, since we could not always find the true value. Okay, so let's talk about accuracy and precision. So as you can see here in this image on the left, we have a tabulation of the comparison of accuracy and precision. If we say something is accurate, it is closer to the target. No? As you can see in letter B, it is both accurate and precise. And then yung B natin, it is a little bit accurate, since it almost hits the targets on average. So how close it is into the true target, that is the accuracy. And then precision will be just basically how spread or how your data is compressed. So the precision is basically this letter C. If your data is clumped together, then it is precise. But if it is both accurate and precise, it will be letter D. Okay. So errors from calculations can be analyzed with regards to their accuracy and precision. Ayan. So let's talk about imprecision first, So imprecision is also called as uncertainty, and the magnitude of is basically the magnitude of scatter. So if your number is a little bit scattery, meaning that it is imprecise. And then inaccuracy is also called as bias, and this is the systematic deviation from the truth. So basically, how close it is from the target, that is accuracy. So therefore, inaccuracy is how far it is from the target. So this error is the sum of both of these components, imprecision and inaccuracy, and we could incorporate imprecision with the use of significant figures. So if we utilize less significant figures, we will introduce more imprecision. But if we utilize more digits or more significant digits, this will be more precise. And then inaccuracy is introduced when we are far from the solution, and it depends on the method. If the method is accurate or inaccurate, or it sometimes the solution might be inaccurate for some time, and then the accuracy will build up over time. Okay, so finding the true error, or E sub t, that is basically the exact value of the error or the absolute value of the error, and doesn't consider the magnitude of the value under examination. So E sub t is equal to true value TB and approximate value TB. So we could find the error in the independent variable x, or the output variable y. So x here is the true value, and x tilde, one with this tilde sign, is the approximate value. Okay, so the error can be normalized. So instead of an absolute value, we could find its relative error. So it could be fractional, or it could be in percentage. So the difference between the two is that in percentage, we're talking about 100% as super accurate, but further down the line of 100%, that will be inaccurate. Okay? All right. So given this function, okay, where f of x cubed minus 2x squared minus 5x plus 6, where x equal to 2, f of 2 is the true value, and x plus a is equal to 1.995. F of 1.995 is approximate value. Find the true error and the percentage relative to error. Okay, so in here we have a given function, and then we are tasked to find the true error and the percentage relative to error based on the assumption that the true value will be the function f of 2 and the approximate value will be the function f of 1.995. So to find this error, okay, so to find this error, we have e sub t that is equal to true value minus approximate value. So the true value is f of 2 and the approximate value is f of 1.995. Okay. So to find f of 2, we have to just substitute this number 2 into our function here. So substitute this 2 here, and then we have f of 2. Substitute the 1.995 to this function, we will get f of 1.995. So let's utilize the calculator effectively. Let's see here. So we have this function. So we have 4x cubed, 4 alpha x cubed, and then minus 2 alpha x squared, and then minus 5 alpha x, and then plus 6. So utilize calc function to substitute the value of x, which is, let's say, calculate 2. So 2, now substituting 2 to our function, we will have 20. No? And then for the other one, substitute 1.995. So 1.995 again. We have 19.83. So in here, I think we will just utilize for the rest of the course about 4 significant figures. We have 19.83. So 4 significant figures in this course. So therefore, this error term, sorry, the true error will be 20 minus this, which is 1745. So sorry, 0.17. Actually, this should be 0.17 only, no? But I guess we will just write things down in 4 significant figures for this course, no? For all of the sequence of your solution. So 0.1745. Okay, so this is your true error. So how do we find the relative or the percentage relative true error? So the percentage relative true error, no, will be equal to the true value minus the approximate value over the true value times 100%. Or in other words, the true value minus the approximate value is the error term e sub t. Okay, so we have here, excuse me, 0.1745 all over the true value, which is 20, and then multiplied by 100%. So let's calculate this again. So we have answer over 20 times 100. So the answer should be 0.08723%. 0.8723%. So this is our percentage relative to error. Okay. Alright. So another example here. Find the numerical derivative of f of x is equal to e raised to 2x at x is equal to 1 and h is equal to 0.02. Solve for the true error and the relative true error. Alright, so what is a numerical derivative? Now, so the numerical derivative, guys, is when instead of finding the derivative using the definition of a derivative, which the limit as delta x, sorry, or h na lang, no? H approaches 0, of this f of x plus h minus f of x over h. So this is the definition of a derivative. We could approximate this by removing this limit and just having a value of h. Okay, so remember this one, guys. So we have f of x, no? So we want to find the numerical derivative, which is basically this, right? So f of x plus h will be f of x. No? So x is equal to 1 and h is equal to 0.03. We have here 1.03. Okay, so for this one. And then minus f of x. So f of 1. And then over h. So h is 0.02. Yeah. Okay, so solve this using your calculator. So how do we do this? So let's use our calculator again. We have here, let's solve for f of 1.03 first. So we have e, so the function is e raised to 2x. And then let's substitute this 1.03. So as you can see here, this is 7.846 or 5, 6. And then minus f of 1. So in here, we can just substitute 1. Okay, so 7.389. 7.389 and then over 0.03. So the numerical derivative, we solve this 1, 7.846 minus 7.389 over 0.03. So the answer should be 15.233. So we have 15.23. So this is your numerical derivative. So this is basically the slope of the function at this given point, approximately. Now we want to find the true error, and the true error here again is equal to the true value minus the approximate value. So what is this? What is this that we actually solved? This 15.23. So this is a numerical derivative, meaning it is an approximate value. So this will be our approximate value, and the true value will be the true derivative. So the true derivative is when we find the derivative of e raised to 2x and substitute the value of 1. So f of 1 or f prime of 1 will be equal to the derivative of this. So the derivative of e raised to 2x is 2 e raised to 2x. Okay. And then substitute this x equal to 1. So x is equal to 1, we just substitute 1 here. So f prime of 1 will be equal to, we have 2 alpha and then raised to 2 times 1. So we have 14.78. So 14.78. What we just solved here is the true value. So this will be our approximate value. This will be our true value. Therefore, the error or the true error will be 14.78 minus 15.23. So the true error will be, so let's just minus this now, 15.23. So we have 0.4519. So negative 0.4519 as our true error. Okay. So to find the relative error, so E or epsilon sub E, that is the error term over the true value times 100. So this will be equal to negative 0.4519 over the true value, which is 14.78 times 100. Dot 100%. Okay. So this will be divided by, okay, we have negative 0.4519 over 14.78. Okay, so we have here multiplied by 100. This is negative 3.058%. So we have here negative 3.058%. So this is your relative true error So on some of the activities that I will give you guys, I will put a true value here. Sometimes I will not put a true value. Sorry, I will not put an absolute value. So if I put an absolute value here, that basically means you have to find the absolute value of this. So you have to remove this negative sign. Okay, so I will not put the absolute value here yet, in this case, but for the next, maybe for the next examples, we will see we should compute the absolute relative to error. Okay, so let's move on to the approximate error. So in actual situations, the true value is rarely available. So in reality, some equations are just not solvable analytically. Meaning analytically, it cannot be solved using, for example, quadratic formula, factoring, no? Or in differential equations, some of the differential equations might be nonlinear and there's no method of solution for that type of differential equation. Therefore, we have to compare our computed value into a previous approximation. So if we have no true value, we do not know the true solution, we could just approximate the error by utilizing the present approximation versus the past approximation. Okay, so T sub A is equal to the present approximation minus the previous approximation. And we could also normalize this approximate error using the fractional relative approximate error and the percentage. So we will usually use the percentage relative approximate error. Okay, so just multiplied by 100%. So what is the denominator here? Always remember, guys, the denominator should be the present approximation. Okay, so the previous error, your true error, the denominator is the true value. In here, the approximate error, with regards to relative approximate error, the denominator should be the present approximation. Okay, so let's say we have a given scenario here again. Okay, we have a given function, and then where x plus a is equal to 1.995, f of 1.995 is the previous approximation, and x plus a is equal to 2.003. So f of 2.003 or f of 2.003 is the present approximate value. So find the approximate error and the percentage relative error. Okay, so in here, if it is not discussed, we should put here approximate. If the context is we could not find the true solution, we should find the approximate relative error. So okay, let's begin with finding the relative error E sub A, which is basically the present approximation minus the past or the previous approximation. So in here, the approximate error is this function. The difference between these two functions, since the present is f of 2.0003 and then the previous approximation is f of 1.995. Okay, so how do we compute this? So utilize your calculators, scientific calculators. Again, we could utilize this function for 4x cubed minus 2x squared minus 5 alpha x plus 6, and then calc. We have here 2.003, no? 2.0003. We have 20.01, and then for the other one, we have 1.995. So substitute 1.995. We have 19.83. So the approximate error will be equal to, we have 20.01 minus 19.83 over, sorry, not over, no, but we have to only subtract, okay? So the approximate error will be 0.18. All right. So to find the relative approximate error, we have epsilon sub a, which is equal to the approximate error over the present. No? So we have here the present is so let's put here 20.01 and then multiplied by 100%. So this will be equal to, we have the answer over 20.01 multiplied by 100. So the answer should be 0.8996. So E sub A 0.8996%. So this is your approximate relative error. All right. So if you would ask for, let's say, if a given equation is unsolvable or it doesn't have a true solution, how do we know if it is correct or how correct is our approximate solution through numerical methods? So, paano yun, no? One criterion that we could use or we could utilize is the Scarborough criterion. So the Scarborough criterion is that we introduce a tolerance in the approximate relative error. So given that your computation needs to be correct at n significant figures, you can find the that your solution will be correct if you utilize this tolerance of epsilon sub s is equal to 0.5 times 10 raised to 2 minus n. So if you substitute n here, which is your number of significant figures of interest, no? So meaning if you want your computation to be what do you call this? Accurate at n significant figures, then you just substitute this n here, and you will get this tolerance. No, and the stopping criterion is based on the Scarborough criterion. Yeah. So let's continue with the errors. No? So let's talk about the round of errors. No? So usually when we are doing the computation, actually what we did last, we introduced round of errors already in our calculation, but since the computations are simple and hindi naman siya marami, no? The computations are not a large quantity, the round of errors are not apparent. But in larger computations, the round of error will be more apparent. So when we utilize numerical methods in the solution formulation, you will encounter that computers cannot store numbers in a realistic way. So usually, the computers will store your number into its base 2. No? So instead of a base 10, which is 1 to 10, the computer will store your data, or the number data, into its base 2 form. So meaning yung ones and zeros, the ones and zeros. So in the conversion from the base 10 to base 2 will already introduce a round of error. Okay? And then if, let's say, your number has infinitely many digits, meaning it is non-terminating, no? So numbers like pi or 1/3 are an example of non-terminating numbers. No? You will have to round them off since your computer does not have an infinite storage of data. So you will have to store your number into a single precision format or a double precision format which is usually accurate between 7 to 8 digits and 15 to 16 digits respectively. So another sources of roundoff errors will be the subtractive cancellation. So let's say you have two numbers that are almost close, no, to one another, and their answer will be approximately equal to 0. So sometimes the computer will cancel everything, no, instead of that remaining terms if the two numbers are close enough. And then if we have large arithmetic computations, so let's say your computation, you're computing 1 million times, no, or 1,000 times, the roundoff will just echo, no. It will accumulate over time during those computations. And then let's say we want to add a large number with a small number. Sometimes a small number will not get considered since it approaches to 0. No? So let's say you add 1 billion with 0.01. The 0.01 will be just approximately 0 if we add these two numbers. No? And then a smearing, when we have a power series or an infinite series that we truncated, usually there is a problem or instability. The solution will oscillate. No? And then the calculation of inner products, so basically your dot products, if you have a large arithmetic computation, you will introduce a lot of cumulative errors. Okay. So let's try to find the roundoff errors of this given numbers. So let's say we want to just find the 4 significant figures. What is the percentage relative error of this given number? So let's see for number 1. So to find for the relative error of E, so we have E, or sorry, true value minus approximate value over true value times 100%. So our approximate value will be when instead of E, we have to assume that it only has 4 significant digits. So we have here E minus, so the approximate value here will be, what is E? No? So 2 point, okay, let's show this. So alpha E, we have 2.718, 2818, and so on. So using 4 significant figures, we have 2.718, okay, and then over E times 100%. So calculating this, your relative true error for the rounding off will be equal to times 100. So the answer should be 0.0137%. So this is a relatively small, no, right? 7%. Okay, so this is a relatively small error. Okay. And then for number 2, let's try to solve this again. So the true value will be this long number minus the rounded off. So we want to round off at 4 significant digits. So we have 2.003. Okay, and then all over the true value 2.003458764. Multiply this by 100%. So the answer should be 3458764 minus 2.603, and then write this again, 58764 multiplied by 100. Okay, so the relative true error will be 0.028 2289%. Right. Sorry. So this should be rounded off, so this will become 90. So the answer is this for number 2, and then for number 3, 2/3. So for the true error of 2/3, when we round this off at 4 significant figures, sorry. So we have 2/3 minus 0.6667 all over 2 over 3 times 100. Okay, we have 2/3 2 over 3 minus 0.6667 over 2/3. Multiply this by 100. The answer should be -5 raised to -3. So basically this is 0.005%. No? Okay, so we could actually introduce here 4 significant figures now. But I think that will be a waste of time. So we will just write this down in this form. So this is actually negative, you know, guys. Yeah. But if you want to find absolute, okay, you will have to remove this sign. Okay. Anyways, let's just show this as negative. Okay. So let's let's reinforce this knowledge that when we're calculating with our computers, we will always introduce round of errors. So anyways, even though errors are apparent in when using computers, there are still clever algorithms that help to minimize them. Okay, so an example of that will be when you add 0.1 1,000 times. Okay, you can utilize a higher precision to minimize this round of error. You know, more precise, although it will introduce more memory and more exhaustive in the computing power. So let's try this one. No, so will there be difference? No? So using MATLAB, if we implement this problem, so we substitute x as a double type of number, and then add this x 1,000 times. As you can see here, this is a for loop wherein we add x 0.1 by 1,000 times. So as you can see here, it is accurate, no, at this scenario. But if we utilize a single type of precision, and we add this again 0.1, or we add this 1,000 times this 0.1, you can see here that there will be some error. So instead of 100, the answer should be 100. We got 99.999. So you can see here the difference, or the comparative difference of utilizing a higher precision data storage compared to a lower precision data storage. Okay. Okay, so for the last one, for error analysis, we have the truncation error. So the truncation error basically is just the result of an approximation in place of an exact mathematical procedure. Okay, so that is a little bit jargonish, but what does it mean when we have an infinite series? Okay, if we have an infinite series, we could truncate this infinite series in place of this infinitely long series to get an approximate answer. And this difference between the true answer and this truncated answer will be the truncation error. So let's demonstrate this idea using this example. So calculating the sign of a number using a finite number of terms from the infinite series will result in truncation error. So if you're wondering how does your calculator calculate sign of a function, no? Or a sign of a number? Actually, what they do here is similar to this, no, not exactly this one, but similar to what Taylor series is for, approximating a function. So they just substitute a value, no? For example, is that we substitute this number x to this infinite series, but we cannot really calculate this infinitely, so we just substitute pieces of this infinite series. So let's say your calculator only computes 20 terms, no? And it will be accurate for about 10 digits, no? For example. So that is basically the accuracy that your calculator can handle. So this could be useful for calculators, no? But actually there are more efficient ways to calculate the sign of a number, and it will be outside of this lecture. So let's try to approximate sine pi over 2. So let's say we substitute this pi over 2 to sine x, which is 90 degrees, or 90, yes, 90 degrees. So sine 90, or sine pi over 2, now the true value of this, if you remember in your trigonometry, is just basically 1. So this is our true value, and let's see if it will approach to this value. Okay, so we can tabulate this truncation. Let's try utilizing one term, or two terms, or three terms, or four terms, and so on. So if we, let's say, utilize only the first term, okay, so if we substitute pi over 2 here to x, we will get this numerical value 1.57, and its true error will be 57.1. Okay, let's make this accurate by adding another term, which will be this. So adding two terms, adding another term will introduce less truncation error. So we will substitute here pi over 2, and then also for x cubed over 3 factorial. So if you calculate this, you will get 0.9248, and your true error, or the relative true error, will be 7.52. And you can continue this, and so on and so forth. If you utilize three terms, the true error will decrease. As you can see here, if you utilize 6 terms, it will be so close to your true value, which is 1. Okay, so that is the idea of approximation by the use of an infinite series. Okay, and the truncation error is basically the error, the difference of the true value of your sine pi over 2 for your function versus the truncated value. Okay, so let's have an example here. So the Maclaurin series e to x is equal to 1 plus x squared plus x squared over 2 factorial plus x cubed over 3 factorial, and so on and so forth, truncated in 4 terms. What is the truncation error? So where did this came from? So this is calculated using the Maclaurin series that we will discuss later. So if we want to find the truncation error, which is basically just the difference, okay, the truncation error, let's just call this R sub n, so this will be familiar later on, which is the true value minus the approximated value for the truncated value. So the true value here will be this infinite series, right? So 1 plus x squared plus x squared, should be, so we have a problem here, banana. It should be x cubed. Let's change this one. It should be x cubed over 2 factorial. Anyways, let's changing this. Okay. All right. So this will be your Maclaurin series. So the true value will be this infinite series of power series, 3 factorial plus x raised to 4 over 4 factorial, and so on and so forth. So this is your true value, and then your approximate value will be the truncation in 4 terms. So instead of adding this infinitely, we'll just utilize this 4 terms. So this will be 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Okay, and if we do this subtraction, as you can see, our truncation R sub n will be equal to, so we can just cancel this out, so that the series that will remain is this x to the 4th power over 4 factorial plus x raised to the 5th over 5 factorial, and so on. So this will be your truncation error. Okay, So that's it. Thank you guys, and let's discuss another more.